or I prepared previously. Number system we saw yesterday. The logic gates. These things, everything is given in these slides. The pin diagrams of 7400, 7402, 2 input NOR gate, then 7408, then 7432, 7486, XOR gate, then NOT gate. So these are the ICs, the integrated circuit chips, whatever we are using in your AD labs. Then some basic explanation about the OR operation and all, how it works. As here the example is given with respect to the bulb and the switches, normal physical switch, whatever you have. These kind of examples are there. You can go through that. The AND operation, how it works. This is the logic. This is the physical connections if you have, like your electrical connections. So these things. The equations which are used for the simplification. You already have this in your DMS. You have a DMS subject in your syllabus. So there also you are going to study this Boolean algebra and all. Simplification. I guess you know all these things. Additive law, multiplicative law, what happens. So go through this. Boolean rules of simplification. So how to simplify the circuits. So one equation will be given, where the equation is A plus AB. Actually, if you are going for a circuit, then this is your circuit. Whether this circuit is necessary, then you go and solve that. A plus AB. So if you do all this, final answer is A. I don't want a AND gate and OR gate. Just the A input is enough. The answer of A plus AB is same like A. So this is the simplification kind of things. Actually, we don't want to do this. Just consider the A signal, A input, that is enough, because the answer, the result of A plus AB is same like A. So this is how we are simplifying the circuits. So these things will come in your lab also. You have to simplify, because we can't do big circuits in your lab. Restricted. We have only 4 slots in the trainer kit. So within that 4 slots, I need to do the experiment. Then I need to simplify it. So directly, if you are going to implement the equation, it will be like a large circuit that time. So your number of logic gates you have to decrease. Here you can see, first one, 2 logic gates are there. Then we are simplifying that. So whenever you are simplifying, you got A, means the A signal directly if you take, that is enough. Second one you can see, it's a large one. First one you can see there are 3 logic gates are there. So here you can see a NOT gate is there, one AND gate is there, OR gate is there. This is the circuit given, the upper part. So A plus A bar B. Then simplify that. Whenever you are simplifying, you got the answer A plus B. Means I don't want 3 logic gates, one OR gate I have and A and B as the signals, then enough. So whatever results generated with A plus A bar B is same like A plus B. So no need to have 3 logic gates, one OR gate is enough. So one question will be there something like this to simplify. So one more simplification you can see here. First, they are given this equation A plus B and A plus C. So A plus B, that is the OR gate, A plus B. Then A plus C, one more OR gate. Then between those two AND operation here means I want an AND gate. If you are directly implementing three logic gates like this, but you simplify that, then you will apply all the Boolean laws and whatever you have, identity law, whatever you have applied. Finally, you will get one simplified equation A plus BC means one AND gate between B and C and one more OR gate between A and B dot C. So these two logic gates are enough actually. Don't want this upper part. These things no need. Only two logic gates. So you may think how much it may cost us to have one more logic gate. Because we have in IC there are four. I can use the circuit whatever I have in the three logic gates. We can use it. Yes, we can use. But the problem is each logic gate, it is a physical component. There is some transistors, all those things will be there in the IC. So each component will be having its own delay. Some error factor, some leakage current, voltage, all those things, then the error factor will be there. So those delays will be having impact. So each IC will give small delay in that. So each logic gate, each transistor, whatever you are using in that, it may have its own delay. So the result generated will be having a more effect on that. Means if there are 10 components or 10 logic gates, imagine 1 millisecond delay in each component. Then 10 millisecond delay will be there when you generate the final result. So we want to rectify all those. We want to minimize the delay. So we are going for a simpler one. Fine. There's one more simplification you can see here. So one equation was given, this one. If you are directly implementing that, you need this big circuit. 3 AND gates, 2 OR gates. So simplify that, all these Boolean laws are applied, then finally we will get B into A plus C. So here I want between A and C, I want one OR gate, and after that AND it with B. So only two basic gates are enough. Fine. So De Morgan's theorems. I guess you know these things. Anyone is not aware of your De Morgan's laws or theorems, whatever we call? You had it in maths. The first one, whenever you are having A dot B whole bar, this we can write it as A bar plus B bar. Then whenever you are having A plus B whole bar, that means A bar and B bar. So don't worry about this negative or negative NAND and all. Later it comes. I'll explain that. The negative logic. There are two things with the whenever we are studying the logic gates, one is the positive logic, one more is the negative logic. It comes later. I'll explain that time. Now don't worry about that. Just remember the De Morgan's theorems or the laws. So here also you can see that applying something to simplify. So A plus BC bar was there. So that simplified, we are applying that De Morgan's theorem. So double bar will be cancelled. Then A bar BC. That is a simplified one. So I'll share these slides with you and the number system. So these are the basic things, whatever we have, that's it. So binary system, whatever we discussed, same things are there. Just go through the slides. The conversions. Octal number system. So position values and all. All those things. 8, 4, 0, 1, 2, 3, all those. Decimal to octal, how to convert and all. So divide that with 8 and all, then the whatever reminders you have that you consider. How to convert binary to octal group with 3 bits. So this is the binary value, these 3 and 7, the next one is 2, the next 3 are 3, and the next 3 will be 5. So like this, that is your octal number, binary to octal. Hexadecimal system. The values, sample values. So go through these 2 slides. One small quiz will be there next Monday or something. You can answer if you go through these 2. Fine. Okay. The marks also will be considered. I guess you can see it is not visible. I guess in classroom only homework section is visible. So next I'll give the quiz in that classroom itself. Fine. We'll go to our. I guess this is enough with the basics. I'll go to module 2, first one. So I'll be doing module 2 now. That is your digital electronics. So module 1 is your analog part, and module 2 to 5 will be the digital part. Fine. So these are the things we have to discuss in this. So your syllabus start somewhere from K-maps. So quickly I'll revise this. Already you know basic gates and all. I'll just skip those things. So we have basic gates, 3, NOT gate, OR gate, AND gate, symbols given. We have copied the pin diagram also. Timing diagram is there in this. Then 2 input OR gate, table, symbol, 3 input OR gate, how it looks like. Then 7432, that is quad 2 input OR gate. Then you have timing diagram of that. Then AND gate. Then 2 input AND gate symbol, table, and the IC diagram 7408. Don't worry, I will share all these slides in the classroom, Google Classroom. You can refer that because already we covered all these things. So universal logic gates, NOR and NAND. So the NOR is also called inverted OR gate. NAND is also one more name, that is inverted AND gate. Logic symbols, table, and NAND gate. See? So there is one more assumption or one more way of understanding the logic. So first one is usual, the positive logic, how we consider. So whenever we are writing binary 0, so that we call it as low voltage, means there is no voltage in the device, no voltage is provided, that is the low. So whenever we are writing 1, we consider that is as high, the voltage high or true. So one more way of understanding that is, so this will be low, this one will be high, or this one is false, this one is true. This is actually whatever we are studying or whatever we have the practice. So 0 means low or false, 1 means high or true. So there is one more way of assuming. So based on the situation, with the same logic gates, OR gate, NAND gate, NOR gate, all the, whatever we have, the logic gates, we can assume the reverse also possible. That is negative logic, whatever we call. That is based on the situation. It is fine. So that time, in the negative logic, 0 will be considered as high, 1 will be considered as low. Fine. Here, whenever you are having 0, that is considered as true, and one more 1 is there, that is considered as false. That's the reverse logic. Fine. So this is also possible. We are not doing any changes in the circuit. Same circuit, same connections, everything is same. But way of understanding, the way of working with the circuit is different. So whenever in some circuits, like your basic electrical connections, whatever you are having at home, the switch is off, then your fan will be in the off state. If switch is on, then the fan will be in the running state, in the on state. That is how it works. Fine. This is one situation. But if you are considering the security related components, some sensors or some switches, if there is a continuous flow in that wire, or the circuit is closed, if door is closed or something like that, the continuous flow is there in that, means it is low, means there is no security threat. If there is any distortion, if there is any disturbance in the connection, that time it will be 0. 0 means low actually, but we are giving one siren. Fine. So that is the positive and negative logic. That is when the positive and negative logic comes to picture. So that is how we want to work with the circuit. Whether the 0 is important for me or 1 is important. Whether low voltage is important for me, high voltage is important. So based on the situation, we are assuming or we are considering the voltages. That's it. Fine. Understood? No? Any doubts with the positive and negative logic? What is that? Okay, come to this one. We will have a little clear picture with this. So this is truth table for OR gate. Fine. A and B are the inputs. Y is output. So A and B both are low. Then output is low. If any one is high or both are high, then the OR gate output will be high. So these three you can see. The first one, both A and B are low. So these things, the next three things, low and high, high and low, and both are high. So this is high and this is low. So this is actual whatever we are following. Means the things, the devices or the electrical connections, whatever we have, all these things follow this one, the usual logic, or the positive logic. Fine. So we'll write low as 0 and high as 1, and low means there is no action, there is no output. 1 means there is some output, there is some action or the work is going on. If you have some component or the agriculture pump and all, no connection, no, they require 3 phases sometimes. So there is no power in one of the phases, then the pump will be in the off state. If all the 3 phases are having proper voltage, then the pump will run. Something like that. So here also it is a positive logic it is. So whenever we are going for the negative, we will reverse this situation. So truth table of OR gate in the negative logic. See, the first table we are not doing any changes. The first table, whatever you are having, this is the first one. This is the second one. The second table follows positive logic. This is the reference. First table is the reference for me. Second table is constructed from the first table using positive logic. Means wherever I have low, I'll write 0, and wherever I have high, I'll write 1. Usual. But the next one, the third table, whatever you see here, it follows negative logic. Means from the first table, wherever I have low, I'll write 1. And where I'll see high, I'll write 0. Fine. I'm taking first table as the reference. This table as my reference. And here I'm doing all those. The understanding is different. The way of understanding this table is different now. Here one kind of regulations or one rules. Means low, if 0 is low is there, write it 0. Wherever high is there, write it 1. But in the second negative logic, reverse it. Wherever you have low, write it 1. Wherever you have high, make it 0. This is your negative logic. So you can see here how it works. The circuit, the table is taken from the OR gate, but the table is now, I can see this looks like a AND gate. 1 and 1, don't go for low and high now. Now go with the values. 1 and 1, 1, 1 and 0, 0, 0 and 1 is 0, 0 and 0 is 0. Just go with the value, don't go with low and high. Now we constructed AND gate from OR gate. How we did that? Just we applied the negative logic. So we have taken the first table, that is from the OR gate. We have taken OR gate circuit or OR gate table. We applied positive logic. We got the OR gate to table. For the same OR gate circuit, we applied negative logic and we got AND gate to table or AND gate circuit. Fine. So this is the use. It is like reusing. I have a circuit. I can make it work for AND gate or I can make it work for OR gate. Only by changing the logic. The way of understanding. That's it. So same circuit I can work for OR gate. It behaves like OR gate whenever you are applying positive logic. Same circuit works for AND gate logic whenever we are applying for negative logic. This is kind of reusability. That's it. No need to build one more circuit, one more diagram and all. Just change the logic. Fine. So similar things you can see in the table also. If you have a positive OR, whenever you are going for negative logic, it becomes AND, negative AND. Whenever you are having AND, if you apply negative logic, it becomes OR. If you are having NOR, it becomes NAND. If you are having NAND, it becomes NOR. This is with respect to positive logic. This is with respect to negative logic. Fine. Any doubts? Anyone is having any doubts? Anything to clarify? Okay, because these positive and negative logic kind of concepts are needed later, so remember this concept. Fine? So if you want recordings of the class, means I can provide. I'll put it in that YouTube channel or somewhere. So you can go through that. You can watch whenever you want. It will be available only for your class. If you want, otherwise, no need. So the assertion level and all, no need, I guess. So I'll explain that whenever you are having lab. For multiplexers and all, we are using the assertion level logic. In your syllabus, it is not there. So in the lab, I'll explain what is the assertion level. So practically, whenever you are working, I'll explain that. Fine. So in some ICs, there will be some bubble for in the diagram. Till now, you didn't got. So whenever you are having some IC, it is having some pins. So they will mark some pins with bubbles, something like that. So if it is IC, this is pin number 1, pin number 2, pin number 3, pin number 4. So what they make is, for some of the pins in the IC diagram, in the pin diagram, they will mark this bubble on round. So it tells that, so whatever signal you want to give it reverse. Because there inside I am negating it. Fine. So if you want to give high, if you want to give high for 1, don't give high, give low, reverse. Because inside I have a bubble, means I have a NOT gate inverter which is inverting whatever signals you are giving. So with respect to your logic, if you want to give high, give it low, because I am making it high inside because of some reasons. Fine. So if you have such connections in the or such bubbles in the pin diagram of any IC, you have to give a reverse signal for that. That is your assertion level. Generally, there's no bubbles will be there in your AND gate, OR gate and all. So in your multiplexer, that is your next module, this assertion level logic comes. There I'll explain, because practically you have to do some experiments in the lab and all. That time you will understand that for enable signals of the multiplexer, always you have to apply this logic. The pins will be inverted. Fine, that is simple. Assertion level logic. That's it. If any IC is having some bubbles, reverse the input. If there is no bubbles, don't reverse. Whatever signal you want to give, directly give it. Fine. So you are having, you don't have HDL now, you are having VHDL. So whatever the circuits you are doing or whatever you are implementing or designing in the lab, same thing you can do in the simulator also. In the next week onwards in the lab and all, we will do the simulations. I'll explain how to do all those things. So here we are using two kind of languages, the HDL, hardware description language, to implement the circuits in software, using some software, Xilinx or Multisim or so many others. So we are using those softwares to implement the circuit. Means it is like before going and taking a real flight as a test trial for a pilot, if you do some failures, then crores of loss will be there. If something goes wrong, what they'll do? They'll sit in a simulator, they'll work there, the different situations, whatever arises during the flight. So those things will be simulated. So harsh landing or the rainy season, how the runway will be wet and all. So those things will be simulated in a simulator and they will run that. And the pilot will, or who is studying, who is in the training phase, they'll train there in the simulator first, so that they will understand how to work, how to operate, what are the protocols they have to follow, all those things. And later, once they are ready, they pass that, then the real plane or someone will use some smaller two-seater wala or something, some private jets or whatever they'll give. Fine. Then only the real, with the real, this one, what is that, planes and all, they will practice. Same thing happens for the circuit also. So whenever you are having a logic, you are building some circuits and all, if you go and do in physical components, you take some ICs and you connect these all things, there will be chances that if some connections will go wrong, then there will be some disasters. Fine? ICs will melt, or some, if we catch fire or something like that will be there. So what you are doing before implementing it is a small circuit, is fine. The larger cases, whenever you are doing for the larger extent, first you are going with the simulation. Use some programming languages, implement that with the language, with the connections, all those things. You had CAD, right, in your first year, first semester or second, computer-aided engineering drawings or something like that. We're designing some bolt nut or some dimensions, whatever, how it looks like from the top view, side view, all those things. That is a simulator, whatever you're using, some tool or solid edge or something like that. The same thing here. We are using some programming languages, and how the ICs will work in a real situation. Same thing we are simulating, and one test bench means where you are running that. You are giving some waveform signals, virtual. You are not actually giving the virtual. So you are giving some high-low values, plus 5 volt, 12 volt, all those things, minus voltage, all those things in a simulator. And the simulator will tell you how it works, how the output comes. Right? So those things you are doing in your Xilinx or Multisim. There we are using HDL languages. There are two types, VHDL and Verilog. So any one we can use in the lab. So I'm using Verilog. I'll give the VHDL codes also for you. I'll explain in the class we have in VHDL. So any one we can use. The Verilogs are easy. VHDL codes are little lengthy, so we are going for Verilog, but I'll give both, I'll explain both, whichever is easy for you, you can follow that. Fine? There are two types in that. So, note down this, okay? The syntax for Verilog HTL. So, these things. This is your syntax for Verilog HTL. Like you have C program has a syntax. You are having header file, or having int main or void main. Then you are writing initialization of your this one. What is the variables? Then printf scanf statements you are writing, import ch or whatever you are writing and closing all those things. That's the same time one format of writing a C program. Similar to that, Verilog HTL is also having its own syntax way of writing. Fine. So here you can see there is a circuit. One box is given. If this box represents your circuit, now is empty. I don't know what is that I am implementing. So box is given. Otherwise, one AND gate, OR gate, or something will be there. Imagine this box as a circuit. Whatever you want to build, a test circuit. It has 3 inputs and 2 outputs. The inputs are A, B, and C. This is the input, and this side is the output. The direction of that arrow mark you can see. So the left side you have A, B, C are input and X, Y are the outputs. There are many outputs, or 2 or more. It is possible. Fine. In that case, to work with this, how to implement the software? There is a syntax. First one, we are writing a module. This is the keyword. Module is the keyword. I am writing a Verilog module. Then give some identifier, give some name for that. This is actually the name. Identifier, no, identifier means some user defined names, whatever they want to give. Fine. Then we list down the ports, input and output. X and Y are output, A, B, C are input. These are called as ports. Port, input port and output port. All we need to note down. Fine. Then semicolon. Then you are listing the inputs separately. Which are the inputs? So keyword is input. Then list down A, B, C, semicolon. Means A, B, C are the inputs. Next, what are the output? Like you are doing C program, int A, int what is that, average or float average, something like that you are doing. Here you are listing input and output. There is no format here, means what is that, int, float and all those things are not there. Here input and output, because everything is a waveform. Fine. Then output keyword, next, output keyword. Then list output ports. X and Y are the outputs for my circuit here. Semicolon. So with respect to your circuit, these A, B, C, X, Y will change. You can give any names for that. Fine. Then whatever you want to do, that you write it. Later we'll explain that. I'll explain the next class and all how to write the body. For some circuits I'll explain. Then it ends with end module. So it started with the module and it ends with end module. This is the syntax. Don't worry much about the Verilog HTL. It is not there in syllabus because we have the lab. For this lab we need this. Fine. So for the class we have VHDL that comes in the module 4, somewhere in module 4. I'll explain the syntax of VHDL also in the next class, because from the next week you have to do the simulation in the lab. I give the softwares, I'll give the links of the softwares. You have to download it in your laptops if you have, and you have to work with that. Fine. Noted the syntax. So any doubts? Anyone is having any doubts? So anything else? Any doubts? Anything to discuss? Nothing, right? So can I ask someone to show their notes? Gautami KM. Gautami, are you there in the class? Okay, fine.
Yes, sir.
Thank you, Gautami. Yes, thanks. Okay. Yajnesh, USN 39.
Yes, sir.
Can you share your notes?
Yes, sir.
Okay, fine, Yajnesh. Thank you. Okay. Whoever is there in the class, just if you are not put any comment in the chat box, just you put your name or something. I'll mark your attendance. Okay. If you already given yes, no, and all, fine. I have already marked your attendance. If you are not commented anything, then just put yes or present in the comment box. I'll mark your attendance. Okay. Thank you. You can leave the session.